Today's lesson looks at the Ford-Fulkerson algorithm for solving the max flow problem. Learning objectives: understanding of graphs as flow networks, the concept of max flow, the Ford-Fulkerson algorithm for calculating max flow in terms of augmentation paths, and its running time and efficiency. Flow networks. A flow network is a directed graph with no negative weight edges and a known capacity. Flow networks have a source vertex and a drain vertex, such that the idea is information passes from the source to the drain. The flow along any given edge never exceeds the capacity of that edge, and the flow leaving a vertex which isn't the source or the drain is always equal to the flow entering that vertex. Flow value. Flow value is defined as the total flow out of the source minus the flow into the source. Ford-Fulkerson algorithm. It is important to be able to calculate the maximum flow for any flow network. This is essentially maximizing the flow value for any graph G. We do this by initializing the flow in G to 0 between all vertices and augmenting the flow along all paths P from S to T. So, in this example, we have a flow network. There is a source and a drain. I've initialized all the flows to 0. So I pick an augmentation path that goes from S to V1 to V2 to T. Now, the maximum amount of data I can push through this augmentation path, or the max amount of flow I can push through the augmentation path, is 14, because 14 is the minimum capacity of the path. So I push 14 through. Then I pick a new augmentation path that passes from S to V1 to V3 to V4 to T. Looking carefully at the remaining capacity from S to V1 in that edge there and the remaining edges, I notice that S to V1 has the minimum capacity remaining, so I can only push 21 more units of flow through the path. So I push 21 more units through the path. Then I pick the third and final augmentation path for this particular instantiation of the algorithm, and I notice that the edge V4 to T has only space for 4 more units of flow, so I can only push along the whole path 4 more units of flow. And so I do, and this gives me a total max flow of 39. Notice that the order in which I pick the augmentation paths here is none too specific in finding the result. The result will be calculated exactly the same. For example, if I had picked S to V1 to V2 to T, then S to V3 to V4 to T, then S to V1 to V3 to V4 to VT, I'd still have found the correct value for max flow, which is 39. Running time. The algorithm's running time is hugely dependent upon the selection of augmenting paths. For example, choosing minimal capacity augmentation paths each time will mean overall max flow calculation requires more iterations to finish. So at any given point, you can view the total max flow as being built up out of iterations of the algorithm, and if you pick minimum additions to the overall flow every time, you're going to require a lot of iterations, which means you're going to get a large running time. The running time for the Ford-Fulkerson algorithm is there given by big O of f in brackets star e, where f is the max flow value. The running time is bounded by this particular function on f, which actually means a bound on the number of iterations required to find the max flow. So the bigger the max flow, the more iterations required, therefore the longer the algorithm will take to finish.